Okay, one of the other hard things that he looked at was inverse functions. So let's have a look at two examples of inverse functions, and I'll keep the first one very simple. Y equals 3x plus 6, or f of x equals y, which equals 3x plus 6. So if we want the inverse of that, one of the ways we can find the inverse is we just swap the x's and y's. So instead of y equals 3x plus 6, we write it as x equals 3y plus 6. And then we make y the subject again. So when we make y the subject, we might take the 6 over and get x minus 6 equals 3y, or y equals x minus 6 all divided by 3. And that's how we find the inverse. So if f of x equals 3x plus 6, the inverse of this, f to the minus 1 of x, equals x minus 6 all over 3. And that's all the inverse is, which is 1/3 of x minus 2. And if we were to graph that, here's the first function, y equals 3x plus 6. Now, this is f of x. If we wanted the inverse function, f minus 1x, I said it was 1/3 of x minus 2. So it crosses at minus 2 here, and its gradient is, or let's say minus 2 there, and its gradient is 1/3. So that would be the inverse function. And if this is the line y equals x, all inverse functions, they have that reflection in the line y equals x. Now, the nice thing about this, because this function is an injective function, it's always increasing, therefore is an injective function. For every y value, there is at most one x value. So it's an injective function. Because it's an injective function, there is no issues with the inverse. The inverse is a function as well. Because it is always increasing, it is injective. In this case, it's also surjective, but really we're only interested in whether it is injective. Let's have a look at another one. We'll look at y equals x squared minus 9. This is not an injective function because here there are two values. Two values. So that horizontal line test fails. But let's look at the inverse first. So we've got f of x, which equals y, which equals x squared minus 9. And I'm going to do exactly the same thing as I did before. To find the inverse, it's going to be x equals y squared minus 9, and we're going to make y the subject. How do we make y the subject? We take the minus 9 over, it becomes x plus 9 equals y squared, or y equals the square root of x plus 9. Now, when we graph this, let's say x was 7. So we put a value in for 7. Or more so when we graph this, if x is 7 in this line, so 7 plus 9 is 16. So y squared equals 16. We have some problems there because y squared equals 16. Y could be minus 4 or y could be 4. So there's a few issues with this inverse function. Why is there some issues? Because this is not an injective function. But the inverse, so this was f of x. So the inverse is the square root of x plus 9. So when x is 0, so what we've got, the inverse, f of minus 1 equals y, which equals the square root of x plus 9. So when x is 0, y is 3. The square root of 9 is 3. When x is, say, 7, it is 4. What about when x is minus 9? When x is minus 9, we get 0. So here, the inverse function would look like this function rotated through or reflected through y equals x But when we graph it, this suddenly is not a function. Because the first function wasn't an injective function, it doesn't have a proper function. This is the inverse, but really when we graph the inverse, we only look at this part of it. Normally, because we would define this as only the positive part. So for f of x to have an inverse, you would say up here that x must be greater than 0. For x greater than 0 or equal to 0, then it has this inverse here. I'll just put that. So the inverse of this function is this function. And the scale's a bit out, but perhaps you can see that that would be a reflection. But that is the nice, easy way of finding an inverse. Just swap the x's and the y's and make y the subject again. Thank you.